So let's give you a quick review for previous class. In lecture 3, actually we talk about the diffusion equation and wants to have some idea about the corresponding solutions for your interesting material systems. So first of all, what can we get from the diffusion equation? We can get a measurable concentration profile as a function of location and time, and also you can. This is for mass transport, but you also can formulate the diffusion equation for heat conduction or the charge transport. And in order to get a measurable temperature distribution and also the electrical potential distribution as a function of location and time. And in the second sections, as long as you have a diffusion equation, in order to solve and get the solutions for your interesting system, so you need to, first of all, you need to determine or tell what kind of boundary condition you are in your material systems. Does it belongs to steady state or non-steady state? And how to tell that depends on the concentration profile or evolution as a function of location and time, whether this concentration profile changes with time. So you can measure the concentration profile at different time points to understand or determine what kind of boundary condition we are dealing with in your experiments. And in the third section, we are going to talk about, because in first and second section, the diffusion equation, the diffusivity in diffusion equation, we assume that the diffusivity is constant. But how about if the diffusivity is no longer constant? If the diffusivity is as a function of concentration of diffusing atoms, how can we determine or obtain this diffusivity? So we are going to introduce you a Boltzmann-Montanaro analysis. At the end of this chapter, we are going to show you if the material system we're dealing with is an isotropic structure, how can we modify the diffusivity? So we are going to tell you the relationship between the crystal symmetry and the diffusivity. So as you know, in these lectures, we put more efforts on mass transport. So how can we get the diffusion equation? Actually, it's from continuity equation for mass transport in solid materials. And also you can use this continuity equation for heat conduction and charge transport to get the corresponding diffusion equation. And you can check in the following slides. But here we put more efforts on mass transport in solid materials. So continuity equation is if you have an interesting material system, a cubic, a bulk of your system, the concentration evolution, the partial C, partial T in this box can be expressed like the generation, the rate of generation or depletion of this mass, this diffusing atoms per univalent, and plus what? This term actually is contribute from surroundings. The atomic flux contribute from surroundings. So we assume in most of the case, for mass transport, there's no generation or depletion happens in your box, your interesting system. So n dot equals to 0. So you can get the partial C, partial T equals to minus atomic flux divergence of atomic flux. And based on fixed first law, you can convert this atomic flux as minus diffusivity concentration gradient. So now you get a diffusion equation, or some people call it the fixed second law. And so we make this assumption. Then next we make the other assumption is the diffusivity is constant. So we can take the diffusivity out, and we got this diffusion equation. So as long as we solve this diffusion equation, we can get the concentration profile as a function of x, location, and time. And now you have successfully get the diffusion equation for mass transport inside the materials. Next, you need to determine what? Determine what kind of boundary condition we are dealing with, or in your material system. Is it a steady state or non-steady state? As we mentioned before, both this no matter it's steady state or non-steady state, there still exists a concentration gradient, right? So, but the difference part is concentration, whether the concentration profile changes with time. So, in order to tell what kind of boundary condition in your material system, so you need to measure the concentration profile in your material system at different time points in order to get whether the concentration profile changes with time. If it does not change with time, like this, you measure this is a dialysis tube, right? And you measure the concentration of diffusing atoms within this dialysis tube. Then you got these curves. And this is at T0. And you also measure the profile at T1, T2, and T3. And you also get the same profile like this. So you can say what? Oh, my system belongs to steady state. Because it belongs to steady state, so it's easy to formulate the concentration profile, right? Like this. And this profile do not change with time, so just one variable, x, location. So this is quite easy if your case belongs to steady state. But however, if your case not belongs to steady state, it belongs to non-steady state. So how can we? Because it belongs to non-steady state, so partial C partial T is not equals to 0. So now you need to solve the partial differentiation equation. This partial differentiation equation, and to get the concentration profile as a function of x and location, right? So in order to get this concentration profile, you can divide it. First of all, you need to determine what kind of material system we are dealing with. And because this is a diffusion process, mass transport, so you need to find out how many driving forces apply on this system to to have a mass flux or atomic flux happens in your material system. As long as you have a flux, when you take the minus divergence of flux, then you can complete this diffusion equation. You will get a diffusion equation for your material system. And in order to solve this, get the concentration profile, you need the initial and boundary conditions. So we are going to introduce you 3 cases commonly observed or happen or seen in your experiments. The first one is we call a diffusion couple. You bind the A material with B material, then you hit this diffusion couple up. Then if we plot the concentration profile of material A, then you can get this step function at T0. So diffusion couple, some people also call it is a step function because at T0, if you plot the concentration profile of material A, will be like a step. This will be a step function. This is for the case 1. And the case 2 is, some people call it is a limited diffusing source. And the characteristic for this case is the surface concentration decrease with time. So it was like this, the concentration is like this, and with increasing time, the surface concentration decrease to here, and get lower and lower, and you can see the diffusing atoms spread, diffuse into this matrix, and right. And the third case, some people call it as unlimited source. Sorry. For the case 2, what is limited source? For example, like you have a second substrate and you deposit a thin layer of diffusing atoms, the very thin layer. So as you heat, and after you heat it up, after you heated materials up, then the atoms is going to diffuse into our second substrate, and because the film is very thin, so consider it's a limited source. So the surface concentration decrease over time because this is a limited diffusing source. And for the third case would be, some people call it as unlimited source. And the characteristic for this case is the surface concentration of diffusing atoms is fixed. So for example, like you have second substrate and you flow the methane, you flow methane, continuously flow the methane, and serving a carbon source. So when you heat this system up, then the carbon atoms will diffuse into the second substrate, and because we continuously flow the methane gas, the gas of methane, so the CS, the surface concentration of carbon is fixed. So with increasing time, it was T1 is here, right? And with increasing time, you can see like the carbon atoms diffuse more and diffuse into deeper region of the second substrate. So for this case is we call it unlimited source, and the characteristic is CS. The surface concentration does not change with time. Okay, so following slide is going to show you how to gather corresponding solutions for these 3 cases. And the point would be you need to find the initial and boundary conditions to solve this diffusion equation, and you can get a concentration profile as a function of location and time. Okay, so let's start from the diffusion equation. This is a fixed second law or diffusion equation we get from the continuity equation in previous slide, and we did make an assumption here, right? The first one would be what? There's no generation or depletion of the diffusing atom in our system. And the second one is we assume diffusivity is constant. So you successfully get this diffusion equation. And this diffusion equation, we call it is a partial differentiation equation with what? With 2 variables, x, location, and t, time. And it's quite difficult to solve this differentiation equation with 2 variables. So in order to convert this PDE to ODE, ordinary differentiation equation, with only 1 variable, so we are going to introduce a dimensionless variable iota. Iota defined as x over square root of 4dt. So we try to convert this diffusion equation to partial c, partial iota, only with 1 variable iota. We try to do this, then we solve this ODE and get the c. Okay, so the first of all, we are going to use the chain rule. What's the chain rule means? Okay, just try to remind you. Chain rule means here partial C, partial T, sorry, and partial T, sorry, a little bit ugly, partial iota, and partial iota, partial C equals to 0. We call this is a chain rule. Then we move these two terms to the right-handed side. Then you got this and this. Okay. Okay, so partial iota, partial t. Iota is equals to this, so you just partial this term with t. So you are going to get the minus iota over 2t, because t, this the powder order is a 2 minus 1/2, right? So you just partial with this one, so you are going to get this one, and you left the partial c, partial iota here, so you can get the you finish the left-handed term. Then we deal with the right-handed term here. Diffusivity is a constant, so we don't need to deal with this. So partial the second deviation of c respected to x can be in c actually. So you just substitute x as square root 40t iota. So you put the square root 40t iota here. So and take the constant 40t out, so you got this. So we use this term to substitute here, and this term to substitute here, and d we drop this term out, so we are going to get the ordinary differentiation equation c as a function of iota. So now we only have one variable. So as long as we solve this, we can get the c, right? So next slide, I'm going to copy these equations. So we got here and show you how to solve this differentiation equation. So we land the q equals to dc over d iota. This is q. So minus 2 iota q, minus 2 iota q equals to, this is a first deviation, it's a second deviation, so it's dq over d iota. So you move the d iota to the left-handed side and q to the right-handed side and take the integral on both sides. So you can get a solution for this equation. Is q equals to a1 exponential minus iota squared. And as you know, q is equals to dc over d iota. So take a look on here. Now we get the solution, right? As long as we move the d iota to the left-handed side, then we can do some integration, right? So depends on what kind of profile we are dealing with. So the first case we are going to dealing with would be the one-dimensional step function like this. This is a step function and is one-dimensional, so it's a step function, and we check the step function. The left-handed side, the concentration is Cl, and right-handed side concentration will be Cr, and this is a typical step function. And at t0, x at 0, so we got this profile step function. So in order to get solve this one, why we need to solve this one? This is typically a diffusion couple profile we just talked about, can be seen in the diffusion couple, right? So we move this one to here and take the integral on both sides, and you got, because the you need to deal with this profile, so you need to get the integral. Integral, this has a bottom limit and the upper limit. So based on this profile, the bottom limit will be negative infinity, then upper limit can be a iota. So you got the c iota minus c minus infinity, and you got this one. right? And if you take a look on this term, it's quite familiar with this, right? It is what you learn previous in the mathematics mathematics books is arrow function. Arrow function z expressed like this is quite similar, right? For this term and this term. And let's some characteristic for arrow function. Arrow function 0 equals to 0. Arrow function infinity equals to 1. So the value of arrow function is between 0 to 1. And arrow function is also an odd function. So arrow function negative z can be expressed like a negative arrow function z. So we are going to dissociate this term into two parts, into minus infinity to 0 and 0 to iota, in order to solve or simplify these results, because we know some characteristic for arrow function, right? Okay, so let's deal with this equation. C iota, we don't know the value. This is what we are interested in. And C minus infinity is what? CL. So you got it. This one is CL. And this term, actually, we use the A2 to represent the relationship between A1. And we try to because we try to link this with arrow function, right? So this term be expressed like this, 2 over square pi. And the rest of term is quite similar to arrow function, right? And this term is just the same. And the rest of parameters will put into the A2. So let's take a look at here. Minus infinity to 0. Because this is odd function, so you can take this minus term out. It will be the minus here. And if you convert it or switch the upper and bottom limit from 0 to infinity, then you got the minus 1, right? Minus 1 times minus 1 is 1. And now the arrow function is arrow function infinity. So now this is 1. And this is equals to arrow function iota. Okay, so you already successfully simplify this equation. And the only unknown parameter would be A1. It's A2, right? But if you substitute the A2 here is the unknown parameter is A1. So next following steps is going to get the value for A1. So we are going to use a boundary condition. We already use a boundary condition for CL, and the other boundary condition will be when the iota approach to infinity, then the concentration equals to CR. So you put this information into here. If arrow function iota is 1, so 1 plus 1 is 2. 2A2 plus CL equals to CR, then you can have A2 equals to this. So you take this A2 back, then after arrangement you got a solution here. Solution here is CR plus CL over 2 plus CR minus CL over 2 times arrow function iota. So this is a solution for this one-dimensional step function. And based on this solution, there are 3 interesting time points. Locations which does not change with time during the diffusion process. The first one is when x equals to 0. When x equals to 0, this term will become arrow function 0 will be equals to 0. So at this point, the concentration profile will be equals to CR plus CL over 2. And these points do not change with time. And there are 2 locations also does not change with time. It's the left-handed side CL and CR. So at positive infinity and negative infinity of these samples, the concentration should keep at CR and CL respectively. So at these 2 points does not change with time as well. So this is some characteristic for these solutions. And by the way, there's one more thing need to remind you. Because we use the boundary condition, this boundary condition is a negative, at minus infinity, the concentration equals to CL. At positive infinity, the concentration equals to CR. And both this location, the concentration at both this location does not change with time. So if in your case, the concentration at the edge, at two ends of your samples, changes with time, then you cannot use these solutions. So if you check the textbook or some other textbook talking about a diffusion process or step function, you know the length of this diffusion couple cannot smaller than diffusion length, square root of 40t, right? If the length here is too small, too short, then the CR and the concentration at two ends will change with time. For example, let me draw something. For example, if it is this short, diffusion couple is like this short, then you can find the diffusion, the material diffuse to the left-handed side, right? And at this end of this material, the concentration is not equals to CL is accumulate, right? So will be increased over time. At this case, you cannot use these solutions because the boundary condition changes. A boundary condition is what you used. You use this boundary condition, this one and this one, to get the solutions. As long as boundary condition changes, then the solution is no longer right. Okay. So this is so first of all, if you want to use these solutions for any step function, you need to check the length of this diffusion couple, whether this length is much larger than diffusion length, square root of 40t. If it's shorter than square root of 40t, then that will cause the boundary condition changes. It's not as you used during the deviation. Okay, and this slide just show you the value for the error function is located in between the 0 and 1, and you can use this table to check the value for error function. Okay, so let's give you an example. Now we have a nickel couple diffusion couple. We have a nickel couple diffusion couple, and it looks like this. The nickel couple alloy, and when you heat these materials up, then there will be interdiffusion happens in between, at the interface, and we know the diffusivity can be expressed as a function of T. Right, and in these questions, they give you a D0 and the activation energy and the Boltzmann constant. As long as you know the T, then you can determine the diffusivity in this material system, right? And at specific temperature, we get the specific diffusivity here. And if you try to plot the diffusion profile of nickel, profile of the copper, Here couple is 0.6, right? 16%. Then you can get this red curve. And first of all, in order to use the solution you learned from previous slide, you need to choose the temperature. Now here is 400 degrees C. Then you use you insert the 673 K here and put the D0 here and activation energy here. You got the diffusivity of copper is expressed like this. But if you want to get the concentration profile, you want to use the solution we get from previous case. First of all, you need to check the length of this diffusion couple, whether the length is much longer than diffusion length or diffusion distance. If yes, then we can make sure. I mean, we can assure that the boundary condition at this location at the right end and the left hand will keep at same concentration, and this concentration does not change with time. Then you can use the solutions. And based on this case, the solution will be what? C0 plus 0 divided by 2 plus C0 minus 0 divided by 2 times error function. So can be expressed like this. Okay. So we successfully get the solutions for diffusion couple. Then next we are going to show you, we are going to talk about the case 2 would be when we deposit a thin film either on the top of substrate or inserted into a matrix. How can we get this the corresponding solutions or diffusion profile of this diffusing atoms? So we are going to starting from this case. Is we inserted the thin layer of diffusing atoms into our matrix. Here we inserted the copper nickel alloy in between the nickel materials, and we try to plot the profile of copper at T0. That means before the diffusion. Then it will be like this, we call it a one-dimensional square function. If our case is like this, can you get the solutions? Actually, from previous case, we know how to we know the solutions for what? For step function, and now it's a square function. So you may think about this. Is that possible to sum up two step function to get this square function? If we can sum them up, then solution, we also can sum the solutions up, then we can get the solutions for this square function. The story is something like this. So we find that actually you can superpose two step function to get this square function, one-dimensional square function. By this blue curve, this is a step function 1 and step function 2, green curves. Both these are step functions. Then let us check whether you sum up these two functions, then you can get this square function. If x below smaller than 0, then you can get 0 plus 0, okay, is 0. And if x is located between 0 and delta x, then C0 plus 0 is C0, okay, it's like this. If x is larger than delta x is C0 plus minus C0 is equals to 0. Okay, it turns out that we can supercompose this step functions to get this one-dimensional square functions. So the solution, we can formulate the solution for blue and green curves respectively, right? Then we just sum them up, then we can get the solutions for this square function. So let's try to do that. For the S1, the curve one, for boundary condition is x smaller than 0, this region, then C equal to the concentration equals to 0. And if Cx larger than 0, then you can get the concentration equal to C0. And the solution for S1 is C0 plus 0 over 2 plus C0 minus 0 over 2 times arrow function iota. And the bottom and upper limit is 0 to iota, 0 to iota somewhere. And for S2 here, you also can formulate the boundary condition. If the x smaller than delta x, concentration will be equals to 0. If x is larger than delta x, the concentration becomes to minus C0. Okay, so you also can get the solutions for this one is what is minus C0 plus 0 over 2 plus minus C0 minus 0 over 2 arrow function iota. And arrow function here, the upper and bottom limit is a little bit need to modify, because this step function, the original point is not the 0. Instead of, it's not a 0 anymore, it becomes delta x. So you need is a shift to delta x from 0 to delta x. So the upper limit should be modified as iota minus delta iota. Okay. So solution for this square function, you can just simply sum this up. So you can get this, just use this plus this, and you drop this turn out, then you got this one minus this one. And you can get this one because you take the C0 over square root of pi out, and you got the arrow function here. But we need to focus on, you need to focus on what? You need to focus on the upper and bottom and upper limit. Then let us check. The first term, actually you integral from 0 to iota. The first term you use you integral from 0 to iota, right? And you minus a similar term but different upper limit. So you minus what? You minus this region. This is iota minus delta iota. So what you left, it left is iota minus delta iota to iota is what you left. So you got this region. It's iota minus delta iota to iota. Okay, so you got this results. Okay? And probably some people were concerned about or ask about but in real world we don't have the a case with negative concentration. So probably some people will, I provided the other solutions for this superposition. You can, instead of you sum these two curves up, how about you can use the minus stuff. So now we have this step function, and we also can list step function minus this green step function. Then you also left this square function. So as long as I get this solution and minus the solution get of this step function, then you can get the solution for this one-dimensional square function. First of all, you need to write down the solution for S1, step function 1. So you can simply write down the C0 plus 0 over 2, C0 minus 0 over 2 arrow function, iota. And the S2 actually, this step function shift from x equals to 0 to x equals to delta x. So the same, the concentration, the profile will be C0 plus 0 over 2, C0 minus 0 over 2. And the arrow function will be a little bit changed. The upper region, instead of iota, because this profile shifted to the right-handed side by delta x, right? So it will be iota minus delta iota. So the solution will be, you just use the solution S1 minus the solution S2. So you got this same results here. Okay? So both ways, both methods can get the same results. Okay, so let's focus on the results here. I just copy these results for the one-dimensional square function, and we try to analyze more about this one-dimensional. We are going to explain more about these solutions. So this solution you can is for this square function, right? It's related to the C0. C0 actually is the initial concentration of diffusing atoms. And the integral region actually from iota minus delta iota to iota actually is integral the thickness of this diffusing source, right? And with this profile. And if we assume the thickness or the length of this diffusing atoms is quite thin, as we mentioned, actually it's a limited diffusion source, right? It's quite thin. So, and we also assume the concentration distribution into this diffusion source is equals to constant. So we can take this integration out and use a delta iota to substitute, right? Because this is delta, if delta iota equals to constant, so this integration, actually you can just put a delta iota here instead of the integration term, right? And what's a delta iota? Iota and delta iota actually is means x over square root 4 dt. So delta iota is equals to delta x over square root 4 dt. And also I use the same to substitute the iota to convert it to x. And next, we are going to, what's the C0 times delta x? C0 is the number of diffusing atom per unit volume, and you times the delta x is actually it's the length or thickness of this source. So we got the ND, and this is a volume density times the length becomes ND becomes the area density. So it's area density into this region, right? So in your textbook, called is area density is a source strength is area density in 1D case, and the ND actually is you can, if you want to get the ND usually is low. You provided this as a diffusion source, right? So we can know the value for ND because you either deposit or provided to this system, right? So ND you can get is from you can integral Cx dx from negative infinity to infinity, And Cx actually is like this. You take this in, and you got this one. And based on this, you can have some idea. The distribution for this ND diffusing atoms is a profile, right? Then you can integral all the profile at any time point. Then you can get the ND. Okay. And also, some people will consider why if emphasize the one-dimensional case. So this is a diffusion source, and as you heat it up, the diffusing atoms either go to left-handed side or go to right-handed side, spread out, right? So it's alone one-dimensional, so it's a 1D case. So 1D case, the concentration profile is expressed like this. And if it is not a one-dimensional case, it's a three-dimensional case. Then three-dimensional case, the solutions should be expressed like x times y axis and times z axis. So you can get these results. And the difference between here is the bottom region. This is 1/2. The power order is 1/2. And this is 3/2. So for 3 cases. And also you can, in order to get the accurate ND, you also can integral this concentration profile along x, y, z. So this is 3D diffusion cases, and this is 3/2, and this is one dimension is 1/2. So what about two-dimensional cases? View 2/2, so it's 1, right? So in your textbook table 5.1, there are 3 different diffusion patterns. The first one is one-dimensional diffusion, two-dimensional, three-dimensional, and this is how we derive the corresponding solutions for one-dimensional diffusion, right? And this is the three-dimensional. As we mentioned, two-dimensional, the power order here, the order here is 1, is 2/2. But some people consider why is the one-dimensional diffusion. Can you explain more? For example, like in this case, is something like we have the planar source diffused into 3-dimensional matrix. So it's a plane source diffused in 3-dimensional cases. And because the profile only change along 1-dimensional, so we call it is a 1-dimensional diffusion. So for example, there are 2 other cases belongs to 1-dimensional diffusion. The first one is point source in 1-dimensional material. So for example, like a point source we deposit in narrow wire, and we heat this up. So the point source, this atom is going to spread out either to the left-handed side or right-handed side, is along 1-dimensional. So this case also is a 1-dimensional case. So you can use the solutions you derive from previous slide, right? And this is point source. So the ND is a number of the atoms, right? And the other cases is the light source. The light source deposit on the thin film. So the light source diffuse out to a plane. And if you plot the diffusion profile, it's only change along 1-dimensional, this dimensional, right? So this is also belong the 1-dimensional diffusion cases. And the source here is the numbers per length, because this you can consider this is a number, because we assume the point source is quite small, so it's a number, and this is the number over length, right? So it's a number of diffusing atom per length, and this is the area, so it's area density. And after process, you can get, you take the ND in the unit here, so you can get the C, the concentration, and the unit will be varied. based on different types of source. So for a three-dimensional, or I mean the two-dimensional cases, like a point source diffuse into two-dimensional matrix. So the point source, for example, if it is a point source here and diffuse into two-dimensional source, so it can be like this, so it will be a two-dimensional diffusion process. And all the other is if we have a three-dimensional matrix, and now we have a line source like this, so diffuses along this direction. So it's a two-dimensional case as well. And three-dimensional case is quite easy, right? Just you put a point source into the point source, so it can be x along x, y, and z. Okay, so it's a diffusion. So no matter what kind of cases, we already know the corresponding solutions, right? We can directly formulate the corresponding solutions of diffusing atoms. Then you can get the concentration of diffusing atoms as a function of x and t. Okay, so let's take a look on the example here. We have a nickel-copper diffusion couple. That means we inserted a diffusing source, a planar diffusing source, in between the pure nickel. And the thickness here is 0.05, and the temperature we know. As long as we know the temperature and D0 and EA activation energy, you can get the diffusivity of copper. And next, in order to use the solution in previous slide, first of all, you need to check what? Because the solution we derive to get the square function is based on the step function, right? And step function, you need to check what? The total length. Whether the total length of this diffusion this material is much larger than diffusion length. And second, you need to check this case belongs to one-dimensional, two-dimensional, three-dimensional. For this case, is diffusion source to the right-handed side or left-handed side. So it belongs to one-dimensional, and one-dimensional is 1/2. So you can use these solutions, and you also can use this to get you can formulate this equation and type every parameters into Excel. Then you can get this profile. It was like a blue curve. Then after 30 minutes, then spread out, and 1 hour and 2 hours, you can see the concentration profile. The concentration decreased over time, and this diffusion source spread out into our matrix. Okay. And so we spend lots of time to deal with when you inserted a diffusion source in between the matrix. Then you can get the solutions here. And if you focus on the layer of diffusion source, you find that the diffusing atoms either during the diffusion process, the diffusing atom either move to the left-handed side or right-handed side. Then you can get this profile, right? But let's back to the case 2. Actually, we are more interested in if you deposit diffusion atoms, a layer of diffusing atoms on the top of your substrate, then you heat this up. What's the solution for this? So are there any relationship between these two cases? Yes. This you inserted a diffusion layer, a layer of diffusing atoms in between the matrix, right? And this is you deposit a layer of diffusing atoms on the top of matrix. So for this atom can either move right to the left-handed side or right-handed side, but for this case only can move to right-handed side. So the concentration profile just double it. So we can get a solution for this case 2. Right? Because all the atoms can only move one direction to the left-hand side. So the concentration then definitely is double it. Okay. So now we successfully get the solutions for case 2.